I'm a grad student at UW-Madison in the electrical engineering department, and this is my work, BlurNet, Defense by Filtering the Feature Maps with my advisor, Miko Lapasti. So typically, adversarial examples have mostly been focused against pixel-based adversaries, but not physical ones. As you can see in the image above, we can add a small amount of noise to the pig, and then it gets misclassified as an airliner. But again, these are not the only types of adversarial examples. One particular attack, known as robust physical perturbations, or RP2, is a way to simulate the physical phenomenon of placing a sticker on a road sign. And in this presentation, we will show some spectral analysis to prove that RP2 attacks introduce high frequency components, and filtering feature maps is more effective than input blurring. And then we also explore multiple loss penalties to see if we can induce low pass filtering behavior in the neural network. And so the broader point that we wish to convey is that defenses should be tailored to defend against a specific class of attacks rather than being universal. So this is an example of a neural network being able to correctly classify a stop sign. But now if we augment the stop sign now with a set of stickers or some graffiti, we see that the neural network misclassifies it as a speed limit sign. So here is a set of frequency plots that I'll be showing. So I've taken the stop sign image and plotted the 2D FFT of the R, G, and B channels, and the same thing with the stop sign perturbed with the stickers. So how to interpret this plot is that the center corresponds to lower frequencies and the edges corresponds to higher frequencies. And the brighter the regions indicate where most of the relevant frequency content is located. So just qualitatively analyzing these spectra, input blurring doesn't necessarily seem to be very effective. But if we analyze the feature maps after we pass these images through the neural network, perhaps we can see a different perspective. So here are a set of unique feature maps taken after the first convolution of the network. The first column corresponds to the stop sign with no stickers, the second one with the sticker. The third is a difference between the natural and adversarial feature map. And then the fourth version is a 5x5 blur kernel applied to this difference image. So the difference image suggests that the perturbations induce high frequency components that are not found in natural stop signs. So this suggests that actually applying low pass filtering at the feature maps might be more effective than applying them on the input. And so this is the finding that motivates our defenses for filtering feature maps rather than performing transformations on the input. So we do this through depthwise convolution. So here in this figure, the red, green, and blue are separate input channels, and the gray are supposed to represent kernels here. And so we hard code for now these kernels to standard blur kernel values, which are shown on the right. And then we also experiment with varying the filter width to see the impact on accuracy. So we conduct a black box transfer evaluation to compare against filtering the input versus filtering the feature maps. And what we do is we generate a set of adversarial examples on one model, and then we can transfer those images over to the substitute model comparing the input versus the feature blurring at the feature maps. So the accuracy here is supposed to represent the accuracy on a victim set of 40 stop signs, and the attack success rate is how good the attacker was. And we see that as you increase the filter width, you do get some marginal gains in the drop for the attack success rate, but the filters are able to see a much higher drop in attack success rate. But unfortunately, you suffer some penalty in accuracy. So can we learn filter parameters so we can actually gain low pass filtering without suffering this degradation in accuracy? So we explored 3 different types of methods using regularization. The first is L-infinity regularization of the depthwise convolution layer. The second is total variation regularization of the layer 1 feature maps. And then the last one is two variants of generalized Tikhonov regularization of layer 1 feature maps. So I'll begin with training the depthwise convolution layer. So the idea is really simple. We just separate the depthwise convolution weights by channel granularity and then apply an L infinity constraint on these weights. So the L infinity norm is a natural choice for these depthwise weights because they'll ensure that the weights in the kernels will take similar values to each other, so very similar to a low-pass filter, as shown below. So the second type of regularization we explore is total variation regularization. The main idea here is that we wish to minimize neighboring differences between neighboring values. And so we directly apply this total variation operation to the first layer feature maps and separating, of course, by batch and by channel. So the idea here is that total variation regularization encourages the neighboring pixel values in the feature maps to be similar so that the high spike introduced by the RP2 attack will be diminished. The last variant of our defenses is based off of Tikhonov regularization. So in the regular case, in the general case where L is, which is called the regularization operator, is the identity, then this degenerates into L2 regularization. But we can actually choose different forms for L. So one such choice could be choosing the identity minus L average or a moving averaging filter. So the idea here is that you want to apply this operator to the feature maps and to extract high frequency components and minimize them. The last defense that we introduce here is choosing the L matrix to be a difference operator, which is supposed to approximate a derivative operation. So when you take a pseudo inverse of a derivative operation, it actually acts as a low pass filter. So we apply this approximate low pass filter to the feature map and then then minimize the resulting product. So we'll refer to this as tick pseudo and the above one as tick HF. So getting to the white box results here, so we plot different configurations for depthwise convolution, total variation regularization, and a tick pseudo. So, and the x-axis here is the L2 dissimilarity distance, or how different an adversarial image is from the regular natural image. The x-axis rate is, of course, how well the attacker performed. So here in this plot, lower to the right is better, and we can see that total variation regularization and both variants of Tikhonov regularization are able to perform reasonably well against these RP2 adversaries. So here's a more comprehensive set of results. So the legitimate accuracy in this table is the accuracy on the LISA test data, the LISA test set, and the average success rate is basically the success rate over the top 18 classes. And the worst case success rate is where the attacker performed the best. And we also compare with randomized smoothing and adversarial training and show that our total variation regularization and TIC-HF are able to outperform these norm-based defenses against these RP2 adversaries. So getting to the adaptive attacks, so the idea is you want to include knowledge of the defense of the attacker. So we try to restrict the perturbations we add to low frequency regimes for L infinity depthwise convolution, since the assumption is that the noise that's added is of high frequency nature. For the other attacks, for the other defenses, what we do is we attach the loss penalty that we used during training to the attacker's objective function and rerun the evaluation. So here are the results from that run. So we see that for 3x3 and 5x5, the success rate went up, and for 7x7, it stayed relatively low at 20%. But the best performing defense here is total variation regularization at 20%, where the success rate only rose by 2.5%. Unfortunately, for both Tikhonov solutions, it seems that the success rate went up by quite a bit, and more careful tuning needs to be done to choose these L matrices correctly. So just to conclude, We showed spectral analysis of feature maps and RP2 attacks introduce high frequency components, and adding low pass filters after the first layers provides some robustness. And we also introduced multiple loss penalties to induce low pass filtering. So for future, we want to extend this idea to larger data sets and larger models. And we also want to combine our regularization terms with methods like adversarial training. And here's the archive link if you're interested in learning more details. So thanks for listening to my talk, and I'm happy to take any questions.